Hi, my name is Summer Chirpic, and this is my 5th physics lab on elastic collisions. The purpose of this lab is to investigate the conservation of linear momentum through the observance of a collision. This lab tracked the collision of two pucks and then compared their change in positions to those of a computational model to see if their collision was elastic. And in the end, my experimental results very closely resembled my computational results, meaning the observed collision was very, very close to being an elastic collision. But first, what are some fundamentals we need to understand? The first of those is Newton's second law, which explains that net force is equal to the change in momentum per change in time. This helps us get the velocity update formula, the average velocity formula, and the position update formula. The second thing we need to understand is the conservation of linear momentum, which states that the change in momentum is zero, and that mass 1 times v1 plus mass 2 times v2 is equal to mass 1 v1 plus mass 2 v2. And for elastic collisions, this means that the change in kinetic energy is zero. To conduct our experiment, I first hit a stationary shuffleboard puck with a moving shuffleboard puck. I then analyzed both of the puck's motions in Tracker, and then simulated the change in position of both of them with a computational model created in GlowScript. I then compared data points that was collected through a graph and drew conclusions. In this experiment, we assumed that the system consists of only the two pucks, and the surroundings consisted of the shuffleboard and everything else on Earth. We assumed that the change in kinetic energy was zero, so it would be an elastic collision. There is only movement in the x direction, and the first puck moves at a constant speed, and friction and air resistance are negligible. So this is the video we recorded, and then we put that into Tracker to analyze the two pucks' motion, and then we got this data. So this red-orange line right here is the first puck, and you can see it moves at a constant velocity before it hits the second puck at around 0.6 seconds, and then kind of moves. It doesn't change in position, so it loses all of its velocity. And this second puck, we see it's not changing position at all until it gets hit, and then it starts to move at a constant velocity. But I wanted to compare that experimental data with that of a computational model. So I took the initial conditions from that the experimental data, to create that computational model. So both of the pucks weighed the same, so they are just represented as 1. This is the position vector of the first puck and its initial velocity, which is equal to the average velocity that it was moving before it hit the second puck. And then this is the initial position of the second puck, and its initial velocity was 0 because it wasn't changing. I then used those principles from before to create this computational model. So you can see when t is less than 0.691, or before the collision, ball 1 is moving at a velocity according to the velocity update formula, and then has a position according to the position update formula. And then when after the collision, we see that ball 1's velocity is now going to be 0, as we assume it's an elastic collision, and ball 2's velocity is according to the momentum principle, and because ball 1 and ball 2, the masses of them are both the same, its velocity is going to be equal to the final velocity of ball 1 before the collision. And so this gives this where we see that all of the velocity of puck 1 was transferred to puck 2. So I then merged both of those graphs to one graph so we can see the data on both sides, and you can see that it very closely resembles. This orange one is the experimental, and this brown line is the computational for puck 1, and then this turquoise line is the computational for puck 2, and this dark blue line is the experimental for puck 2. And because they very closely resemble each other, we can say this is really close to being an elastic collision. But it wasn't fully an elastic collision because of these sources of error. First of all, the second puck slid out of frame, so I was not able to fully see if it reflected the near constant velocity that the first puck had, and it could account for that curve at the end. Also, friction and air resistance were there in the real world, and I couldn't completely consider them negligible. There could have also been tracker mistakes, and only the x direction was considered, because we can see in the video the second puck appeared to move in the y direction as the first puck did not hit it completely head on. So what does this mean? Does the second block have the velocity of the first block? No, it doesn't. It's actually a little less. And this is because air resistance and the forces of the surroundings was impacting the puck, even though in our computational model we assumed it didn't. So we do see a slight loss in kinetic energy as energy was transferred between the two pucks. And what if both pucks were moving? While both pucks were moving, we would see them both hit each other and then move away at a somewhat constant velocity, which we see in this video here. So as a recap, my data very closely resembled that of elastic collision. Its differences were likely due to friction, air resistance, and the fact that the first puck did not hit the second puck head-on. And overall, my experiment achieved its goal of exemplifying the conservation of momentum. Thank you.